Assalamualaikum, students and friends. In this episode, we take a revisit of the concepts of inductive and capacitive reactances and how they affect the impedance in an AC circuit. So just stick around, watch and learn. The question is, in the series circuit shown, the resistance is 255 ohms. The inductance is 45.0 millihenry. The capacitance is 0.400 microfarad, and the source has voltage amplitude 55.0 volts. The inductive reactance is equal to the resistance. Find letter A, the frequency of the source, letter B, the impedance, letter C, the current amplitude, letter D, the phase angle, and letter E, determine whether the source voltage leads or lags the current. As shown in the figure, we have the circuit diagram of an RLC AC circuit, right? Consisting of a voltage source, okay, with a voltage Vs or source voltage equal to 55.0 volts. And the resistance big R is 255 ohms. The inductance capital L equals 45.0 millihenry. And the capacitance big C equals 0.400 microfarad. And we're also given the what we call inductive reactance, denoted by capital X of L, equal to 255 ohms. The target variables are, in part A, the frequency F of the source. In part B, the impedance, capital Z. In part C, the current amplitude, capital I. In part D, the phase angle, denoted by the Greek letter phi. And in part E, we have to determine whether the source voltage, capital V sub S, leads or lags the current, capital I. So for our solution, starting with finding the frequency F of the source using the formula F equals omega divided by 2 pi, where omega is the angular frequency that is not given in the problem, right? So we need to first determine this angular frequency omega using the fact that the inductive reactance X of L, okay, which is given in the problem 255 ohms, and that is equal to the product of the angular frequency omega and the inductance capital L, right? So we can determine the angular frequency omega by just isolating it, right? And come up with the formula omega is equal to the inductive reactance X of L divided by the given inductance. That is, omega equals 255 ohms divided by 45.0 raised to the negative 3 Henry, which simplifies to 5.67 raised to the third power radian per second. All right? So now that we know the angular frequency, we can proceed in determining the frequency f of the source, right? So f is just equal to 5.67 raised to the third power radian per second. That's the value of omega. And then divide it by 2 pi, all right? Which is equal to 902 hertz in 3 significant figures. So this is the value of the frequency of the source, which of course implies that um, in an alternating circuit, okay, we can imagine that the current and the voltage are in fact oscillating sinusoidally, all right, at, at a frequency 902 hertz. At this point, we also determine the value of the capacitive reactance X sub C, which is just equal to the reciprocal of the product of the angular frequency omega and the capacitance C. That is, X sub C is just equal to 1 over 5.67 raised to the third power radian per second multiplied by uh, the given capacitance, 4.00 raised to the negative 7 power farad. So doing our math, we get the value of the capacitive reactance equal to 441 ohms, rounded also to 3 significant figures. Moving on now to our computation of the impedance capital Z. This is now in part B. All right, whose formula is capital Z equals the square root of big R squared plus the square of the difference between X of L and X of Z. So when we substitute the given quantities, we get capital C, or the impedance, equals the square root of 255 ohms squared plus 255 ohms minus 441 ohms, and then their difference will be squared. So when we simplify, we get the value of the impedance, capital Z, equal to 316 ohms, also rounded to 3 significant figures. In part C, finding the current amplitude, capital I, that's simply dividing the voltage amplitude, or in fact, this is also the source voltage Vs, or V sub S, and then divide it by the impedance, capital Z. That is 55.0 volts divided by 316 ohms. And we will get the current amplitude, capital I, equal to 174 milliamperes. In part D, okay, finding the what we call phase angle, all right, denoted by the Greek letter phi. So the formula for that is angle P is just equal to the arctan, or the inverse tangent of the ratio x of L minus x of C divided by the big R. That is, angle phi equals the inverse of the tangent 255 ohms minus 441 ohms divided by 255 ohms. So with the help of your cycle, we get the value of the phase angle phi equal to negative 36.1 degrees, also rounded to 3 significant figures. Last but not the least, in part E, the value of the phase angle phi is negative 36.1 degrees. So this means that the source voltage Vs lags the current by 36.1 degrees. As shown in the figure, we have the current phasor, capital I, the one that is represented by the black arrow, and the source voltage phasor, okay, V sub S. Both phasors are drawn in the first quadrant. Here, the inductive reactance X of L is less than the capacitive reactance X of C, right? The computed phase angle phi, which is negative 36.1 degrees, all right, suggests that the source voltage, or the V sub S, is 36.1 degrees measured clockwise from the current phasor. Thus, we say that the source voltage phasor lags the current phasor by 36.1 degrees. So that ends our lesson. Mabuhay! Till the next episode. MashaAllah. Thank you very much for your indulgence.